It's a pleasure, I was saying, to have in a Alberto Ohashi from Universidade de Brasília that will present Leao and Sousa on optimal stopping of non-Markovian systems. So, sorry for the microphone. Please.
Yes. So thank you very much, Ernesto, for the invitation. It's a pleasure to speak, even though it's online. Okay, so today I'm going to talk about a paper, joint work with Leão and Sousa. So this paper, it's a result of research for many years, and it's a product as a consequence of some results that I got in the context of stochastic calculus for path-dependent problems. And in this work, we're going to apply for stochastic control problem, in a stochastic control problem. Okay, so let me start with the basic question. So the question is, so I'm sorry, I have to find my mobile phone. Just a second. So the basic question is the following. So let's consider psi is Borel functional, which can be the domain of this function is the set of continuous functions. And I consider f a filtration. It can be will be generated by a multidimensional Brownian motion. And I consider U as a set of controls, stochastic controls, taking values in this compact set. It's a compact set on a multidimensional Euclidean space. And then I consider X is a process, but it has to be controlled by a family of processes belonging to U, capital U. And then we are interested in the following stochastic control problem. The sup of this expectation, psi can depend on the whole path of X, and X phi is a controlled process. Okay, and phi belongs to capital U. So this is the classical stochastic control problem. And the question is the following. So in this general setting, I want to answer the following question. For a given error bound, epsilon, greater or equal to 0, how to compute optimal controls which realize this inequality. Okay, so under my integrability condition, obviously, we can always, there exists at least one control which realizes this inequality here. So the question is how to compute them. So this is a very difficult question. And in this general situation, so let me start with some general considerations about literature. The characterization of the value process. What is the value process? So at this stage, I just want to say that the value process is essential sup of this psi x phi and conditioning with respect to some filtration. Okay, so the characterization of this value process, you can evaluate this value process by means of many alternatives. For instance, BSDEs, backward SDEs, and also more modern approach based on quasi-shear analysis, and there are many works in this direction. The characterization, theoretical characterization of the value process, which gives the supreme, the sup of this set of numbers here. Okay, in terms of numerical methods beyond PDE, because stochastic control, there is a deep connection with PDEs, and by means of Hamilton-Jacobi-Bellman equation. So there are a large number of papers dealing with this kind of methodology. But beyond PDE, there are the classical work by Kushner and Depuis, and also more recent approach based on the works by Tuzi and Fan and others. Okay, beyond the Markovian context, there are some works. So to my knowledge, only 3 works dealing with numerical methods for non-Markovian stochastic control. Dolinsky in the context of G-expectation, and Tan in the context of controlled SDEs driven by Brownian motion. It's very nice papers. And also Jianfeng Zhang and co-authors and Han, they work in the context of path-dependent PDEs for, again, controlled SDEs driven by Brownian motion. Okay, so the contribution of this work is we develop a systematical way to compute optimal contours based on the transition probabilities, which drives the non-Markovian path-dependent system. So our approach is based on one unfixed probability measure, which is the Wiener measure. And our methodology applies to any controlled state process, including non-semimartingales adapted with respect to a given Brownian filtration. And we obtain convergence rate without assuming differentiability on the value process. So this is an important point here, because value process, it's difficult to assume, or it's difficult to imagine concrete examples with differentiability assumption in terms of the value process. For people who are familiar with the Markovian case, the value process can be reduced to the value function, which is the solution of a PDE. And we consider the PDE in terms of viscosity solution sense. Okay, so it's difficult to assume this kind of differentiability, even in the Markovian case. Okay, so to our knowledge, this is the first method to solve numerically stochastic control problems beyond Markovian states. Okay, so the typical example that it fits into the theory is there are 3 examples. Probably I will not have time to discuss all of them, but I'll try to discuss the first two. The controlled state given by a controlled SDE driven by the Brownian motion. So this is a path-dependent SDE, because the coefficient here can depend on the whole path of the solution, and U is the control, is the control process. And equation 2 is a different type of non-Markovianity, because the lack of Markov property comes from the driving noise. So the driving noise is the fractional Brownian motion. Okay, and the third one, it's a rough stochastic volatility model. So probably I will not have time to discuss it, but it also includes into our framework. And BH is a fractional Brownian motion. In the Hurst exponent here is between 0 and 1. So the more challenging situation would be when the Hurst exponent is less than 1/2. So we will discuss this in detail. Okay, so as I mentioned, so let me start to present the framework before, and later I will present the main results. So what is the framework? So the framework is, I consider the state value instead of the controlled state process. For me, the more important state is given by the Brownian motion. So the Brownian motion, you can interpret this as an infinite dimensional state, which drives the system. So everything here is a function of the Brownian motion. So I don't want to consider the state itself. The state for me is just a functional of the Brownian motion. Of course, that's infinite dimensional. There is a dependence with respect to the Brownian motion, and the dependence can be very complicated. So I'm going to fix a d-dimensional Brownian motion, let's say in the canonical Wiener space, and F is the filtration generated by the Brownian motion. So so let me start with some notation. So LP is the Banach space of adapted process. Keep it with this norm. And so this dark B here is the expectation when the sup norm to the power of P. Okay, so throughout this talk, you can always interpret capital X as the controlled state. Okay, so for us, a controlled Wiener functional is a map. The domain is the set of controls taking values in LP, such that for each U and S, so this family of process here, it depends only on the control U between 0 and T. Okay, and we are going to consider only continuous process. So for each U, X it has continuous paths. Okay, so for me, a controlled Wiener function is just a map satisfying these conditions here. Okay, as I said, you should interpret capital X as the controlled state which drives the stochastic control problem. So there are two standing assumptions that I'm going to assume, assumption A1 and B1. So D is the space of Cadillac paths taking values on Rn. So assumption A1 is Hilbert continuity of my payoff and gamma between 0 and 1. And assumption B1, is a dependence of the state controlled process in terms of the L2. So B2 is remember that this is the sup norm. And so I'm assuming that there's a continuity of the controlled state respect to L2. Okay. So you will see that assumption B1 it holds for a large class of process. For instance, if you think about in terms of BDG inequality, Burkholder inequality, then you can easily realize that assumption B1 is not strong. It's not strong at all. Okay, so the basic object that encodes the whole stochastic control problem is given by the value process. So the value process, the essential sup of the payoff. So I'm sorry, I'm going to change the notation here. Psi x. So that is the payoff applied to the functional. So here the notation is the concatenation of the control U with V. So this concatenation means that before time t, it's U. After time t is V. Okay, so this is the notation that I'm using here. And condition with respect to the Brownian motion filtration. Okay, so it's important to stress here that the filtration is not generated by the state process. It is generated by the Brownian motion. Okay, so by using the standard properties of the essential sup, so when t equals 0, then we recover the sup of the expectations here. Okay, so this is the value process. So there are two directions at least to tackle this question. So one would be to characterize the value process in terms of BSDEs, second order BSDEs, whatever. But our focus is I want to design a numerical scheme to compute this number here. Okay, and the way we do is to discretize everything. Okay, so our discretization will be based on as I said before, the Brownian motion. and it will be based on a sequence of heating times that I'm described here. So you choose.
But Alberto, let me ask.
Yes, Ernesto?
We are now listening you, Ernesto.
In the case of fractional growth, what is the filtration?
The Brownian motion filtration. So everything is I will refer to the Brownian motion filtration.
And you construct the fractional as an integral of the usual Brownian motion. This is the.
For instance, yes.
Okay, thanks.
Okay, so the filtration scheme, it's a bit, and also the space, and okay, so the heating times are given by this. So when n equals to 1, I consider the first time when the Brownian multidimensional Brownian motion hits this level, epsilon k. And epsilon k is you choose a priori the sequence which goes to 0. And then I define AK, which is a continuous time random walk. This is a continuous time random walk driven by these heating times here. So the increments in the one-dimensional case, which is maybe it's I think it's better to shift to one-dimensional case to understand. So in the multidimensional case, what is the situation? So by strong Markov property, so you consider the first heating time when the Brownian motion hits this level, and then you make a shift, and then you consider the shift Brownian motion, and what you get is the increments of these heating times. They are IID random variables, and you see I'm discretizing the time and also the space of the Brownian motion. Okay, this would be important to reduce the dimension of my problem, because it's an infinite dimensional problem. Okay, so in the multidimensional case, this is the Euclidean norm, but I'm still able to define these heating times and this continuous family of continuous time random walks. Okay, right. So the filtration plays a key role in this work, because remember that the value process, I discretize the value process in terms of I will discretize the value process, and the value process depends on the filtration, and the filtration is the Brownian motion filtration. So it's important to notice that if I discretize the Brownian motion by means of the standard discretization scheme, it doesn't work, because, for instance, if I discretize the Brownian motion in deterministic times, so what we get is still a filtration, which is generated by the whole Brownian motion history between, let's say, two deterministic times, and still an infinite dimensional problem. So the idea here is to reduce the dimension in such a way that to design a numerical scheme. So I discretize the filtration as well. So Fk is the filtration generated by the continuous time random walk, and Fk is just the P augmentation of this filtration. Okay, so this filtration is nice because I mean, I think it was Shirayev and also Jean Jacot. They wrote a paper. They call this a jumping filtration, because between two stopping times, it's essentially, it doesn't move, roughly speaking. Okay, it's a nice, and every martingale in this filtration, it's boundary variation, but it's not really important for this talk. So I will call this discrete type skeleton for the Brownian motion. So yes, so D is a discrete type skeleton for the Brownian motion. So my numerical scheme will be based on this D. Okay. Okay, I'm sorry. I have there are some heavy notation that I have to include in this talk. I cannot avoid. I'm sorry. So IKO is this set encodes the coordinate of the Brownian motion, which first hits the level epsilon k. So so is the set of numbers I1 till ID, IL minus 1, 0, and 1, and the sum is equal to 1. This means that only one coordinate jumps, let's say. Okay. And IK, this is a set which encodes the increments of the continuous time random walk. Because, for instance, if the first coordinate of the Brownian motion hits first the level, then the increments will be epsilon k times I. And I can be either 1 or minus 1. If the first coordinate was not the first coordinate which hits the level, then the increments would be between epsilon k times z1, and z1 is a number between minus 1 and 1. Okay, and then the notation is sk is the ik times the 0 to infinity. 0 to infinity is the range of the heating times. The heating times can be any number, can take values on the 0 and plus infinity. And the elements of S and K will be denoted by this dark B. And yes, S is the element of SK, little s, and I tilde K is the element of IK. Okay, so I also need at eta. Eta is a d-dimensional discrete time process, which essentially encodes the increments of the Brownian motion in these heating times here. And this AKN, I consider the whole information, the information which comes from the increments of the heating times and also the jumps of the multidimensional random walk until time n. And I always consider FK TKN with the sigma algebra generated by this discrete time process. Okay, so the law of the system, I will not enter into detail, but the law of the system can be explicitly computed, and it will be given by this product measure, where nu k is the law of the first heating times and eta k1. So remember that eta k1 is the increments of the Brownian motion between 0 and the first heating time tk1. Okay. Okay, so it is also important in our discretization by the very nature of the problem. So I don't want to work with the controller process adapted to the Brownian motion filtration. So obviously I need to discretize the set of controls. And the obvious choice is to consider stepwise constant process and in a predictable way. So this is a left continuous process, and it jumps only on these heating times. And the jumps, they are with the decent measurability condition. Okay. Another notation is which is reminiscent from the notation concatenation, right? Because the concatenation here means that before TKN, it behaves like UK, and after it behaves like VK. And this is the discrete set of controls that we are going to consider. Okay. So since I'm discretizing the time in terms of the heating times, it's not obvious how to know a priori the number of heating times that I have to consider in my stochastic control problem, because capital T is the terminal value of our stochastic control problem, but I'm not going to work with capital T. I have to work with a heating time Tk of the form Tkn. So it's not obvious to choose what is the final natural number of Tk of the heating, a sequence of heating times, because the heating times is random. They are random. So this number here encodes the number of heating times that I will consider in my discretization scheme. And so this number here in the one-dimensional case is just one. So intuitively speaking, this is the number of periods that I will consider in my stochastic control problem. And roughly speaking, is the order of epsilon minus 2. So it blows up of this order here. Okay. Yes, another notation is the OT is the set of Cadillac process, which jumps only in these heating times here. Okay, so remember that there is a definition of definition here. Let me come back. Controller Wiener function. So I need to replace this function, this notion with respect to not the Brownian motion filtration, but with respect to the continuous time random walk. So this is the replacement. I will call control embedded this structure, which depends on the D, which is the skeleton of the Brownian motion. And yes, so this condition here is just a replacement of the notion of continuous control Wiener function. So everything here is based on the continuous time random walk, including the controls here. Okay, so I will call strongly controlled Wiener functional is a pair X. Remember that pair X you should interpret as a controlled state, and X, calligraphic X is xk, which is the control embedded structure, and I will call strongly controlled if this convergence holds. So we have the typical example is when the X is a controller SDEs driven by possibly singular Brownian motion functions like a fractional Brownian motion. Okay. So the task is, so if you interpret X as a controlled state, so this embedded discrete structure, calligraphic X, you have to construct it. You have to find this sequence of process which converge in this sense. Okay. There are many examples where you are able to construct this family, and with this property here, I will call strongly controlled Wiener function. Okay, so what is the idea? The idea is okay. Let's assume that I have controlled Wiener function, strongly controlled. I will choose an embedded structure, which is based on D. And I will discretize everything. This is a very natural, approach, no? Because I will discretize the value process. The essential soup is the same essential soup as before, but everything is replaced by the continuous time random walk information and the set of controls, of course. I will call VK. Right. So the first result is the dynamic programming equation for the problem. So I need some additional notation. So HK is the action space, which is the set where my stochastic control taking values, and SK, which I have defined previously. And I will add the information of the controls. This is essentially the meaning of this OKN. And Xi is I will add the information of the stochastic control together with the information of the random walk. Okay, so now I'm going to describe the dynamic programming principle, which will be the key step in solving the problem. So the first observation is that once you have a discrete embedded discrete structure, so once you have designed this process here, then very naturally you will have a pathwise version of this object here. You can see here, you can see this object concretely in the Euler-Maruyama scheme, for instance. So the first step is, the first observation is that you can always, you can easily construct a Borel function which represent pathwisely the state, the control state. So we will see that gamma here, it's really, you can easily get this functional. For instance, Euler-Maruyama would be a concrete example. Okay, so to simplify the notation, M would be AKT, capital T, is the number of periods that I will consider in my discrete stochastic control problem. So the final condition is given by the payoff applied to the state. Everything here is pathwise, but it's pathwise in my world, in the world of continuous time random walk, not in the Brownian motion world. And I do this, I define the value of functionals in the backward sense. I will start with this final condition, and then I consider capital U, and I take the sup with respect to theta. And the function here is the optimal state action value function. So this you can approach by means of regression methods. Okay. And again, the filtration is generated by the continuous time random walk, but I also discretize the time. It's really a discrete time process. So this is dynamic programming principle associated to the continuous time stochastic control problem. And the first theorem is the following. So consider the value process, which is a sense of sup of this family of conditional expectations. F is the Brownian motion filtration. Let's assume that assumption A1 and B1 hold true. And let's VK is the value process associated with the embedded discrete structure X. Then equation 6 holds. What is the meaning of equation 6? This is when you try to solve a stochastic control problem, especially in this abstract situation, the first task, and it's not easy, but the first task you have to do is to replace the essential sup with the sup. Otherwise, it would be completely useless, your characterization, because you cannot work with essential sup when you want to design a numerical scheme. So you have to replace, and you have to the relaxation soup with soup. And you see, I consider here the soup in the finite dimensional space. So the v inside the integral is defined in the previous slide. And nu k is the measure. So we have this explicit form of this measure. You can simulate the law of this measure. We also have a concrete explicit definition for explicit formula for this measure. So equation 6 is the first step, is the characterization of the value process in the discrete level. Okay, continuation of theorem 1. So I consider the initial condition of the value process, the discrete one, which is the soup of this family of expectation. And we get a rate of convergence. And there exists a constant c, which does not depend on epsilon, and k. So I give a epsilon bigger than 0, and gamma is the Helder parameter of the payoff. And what we get this rate of convergence here, which depends on epsilon, a constant which depends on epsilon, and epsilon k, which is the sequence of my discretization, Brownian motion discretization to the power of gamma. So this is the first result. All right. So I think that so if you have time, we can discuss the proof. So let me shift to the second result, which is the what is the rate of convergence for the optimal control. So assume the same assumption in theorem 1. And let's assume that we have a rate of convergence for discretization of the state control process. Let's say hk. So for a given arrow bound, epsilon bigger than 0, let's consider phi star k epsilon be an optimal control associated with this control problem here, which can be calculated via 6. Okay. Yes. Then for gamma between 0 and 1, we have this rate of convergence here. So this means these two theorems means that how can we interpret these two theorems? Okay, so you have a stochastic control problem written yes. So we have a stochastic control problem, and I want to find stochastic control which realize maybe not this equality, but up to an epsilon term. Epsilon optimal control problem. Epsilon optimal control. Sorry. And then what you do is okay. So I will interpret this problem. I will replace the Brownian motion in terms of the random walk, and I will treat the problem based on this noise. So everything all the functionals that I consider. So the x, the controller process, the main one, everything is a functional of the continuous time random walk, rather than the Brownian motion. Okay. And the way we discretize, we are able to reduce the problem in a finite dimensional case. Again, if you discretize the Brownian motion in discrete in a discrete grid is not going to reduce the dimension of the problem. So the way we reduce the dimension of the problem by discretizing the time and space. Okay, so when you interpret the problem like this, then what you do is to solve the problem by means of this dynamic problem principle, and we present here the precise rate of convergence. Okay. All right. So let me present two applications. So I try to present out as well the case of the optimal stopping. So let's consider the simplest case, which is still not trivial. The SDE driven by Brownian motion, and it's a path-dependent SDE. It's a non-Markovian. So okay, so my notation here, it's the subscript T. It means that the whole history of a path until T. Okay, so this is the notation. So this is the path-dependent SDE. The coefficients here, it depends on the path of the solution. So what is the embedded disk structure? What is the embedded disk structure? The embedded disk structure is just the Euler-Markovian scheme, but I consider the Euler-Markovian scheme written in terms of the continuous time random walk. Okay, it's not a discretization of the Brownian motion in a discrete grid. So this the embedded disk structure in my world is just the Euler-Markovian scheme. So the typical assumption that I'm assuming here, it's I mean, it's not the mild assumption, is is Lipschitz continuity, and I take into account the whole information. This is standard in the literature. And so according to the two theorems, what we have to do is to compute the rate of convergence of the my discretization with respect to the control state. So we have to find HK. So in this case, HK is given by this. You choose eta sequence with this grow conditions, which is a function of epsilon k. Remember that epsilon k is the sequence of which is associated with the discretization of the Brownian motion, and also I get this logarithm scale here, which comes from the Euler-Markovian scheme. And the other application is the fractional Brownian motion case. So in the fractional Brownian motion case, the state, it's linear, not linear, it's non-linear in the drift. But unfortunately, at this moment, so far, we are not able to put the control on the diffusion part of the equation. So it's a highly non-trivial question how to consider the most complete case. But at least on the drift, we are able to treat the problem. So the main difficulty is, I just want to stress that the dependence of the fractional Brownian motion with respect to the Brownian motion, it's very singular, because this is the classical way to write, one of the ways to write the fractional Brownian motion. You will refer to the Brownian motion. And so this kernel here is very singular, especially when h is less than 1/2. And okay, so this is the main difficulty. Okay, so KH is the kernel. You can write like this. And the way we discretize the fractional Brownian motion is a bit unusual. But yeah, we are not able to discretize in the obvious way. Let's say DAK. because you see, so the problem here is that would be a Lebesgue-Stutz integral. That depends on t and t here, so it doesn't work when you consider dak. So you have to find a more clever way to discretize the problem, the fractional Brownian motion. So I'm not entering into details. So we can discuss later this discretization scheme for the fractional Brownian motion. But the message here that I want to give is what is the embedded discrete structure behind the problem is Euler-Maruyam scheme, but here the noise is the fractional Brownian motion, the discretized fractional Brownian motion in terms of continuous time run walk. So essentially, so we can prove that this approximation driven by continuous time run walk, it converges to the fractional Brownian motion very well. Okay, and the rate of convergence is given by hk, right? In this situation.
So the rate does not depend on Hertz parameter, on h?
It depends on the h parameter through delta and lambda. So for a given h, you fix a pair. So this result here is between 0 and 1/2. So you fix a pair, delta and lambda, such that you have to choose this way, and it depends on h.
Okay, thanks.
So this is the rough stochastic volatility case. I will shift this. Okay, so let's start with some numerical results. I'm sorry, I'm not specialist in numerical simulations, but it's just a very simple experiment. So the problem is, so this is the classical problem in mathematical finance, and let's consider two-dimensional asset price process, geometric Brownian motion. And I want to minimize this quantity here. It's we call this the mean variance hedging, right? The mean variance hedge. So C is the capital, and X is the controlled state, which is the health process, right? And this variables, two variables here, it's denotes the asset price, the risk asset price. So this is the classical problem. Obviously, it's Markovian, and you can solve by PDE, for instance. So I want to minimize this quantity here. So in this example, I will choose as a payoff functional phi. That's maximum European call option, and A bar it's 1. It's the controllers take values on -1 and 1, and it is well known there is a unique choice C star and phi star, such that this infimum is equals to 0. So there is C and phi star, which realize this inequality here, where C star, the optimal capital, is Black-Scholes, not really Black-Scholes, the formula. I don't remember, it's a paper. So in the literature, you can find this closed form solution, okay? Because it's not really an European call option, it's Y minus Z. European, but I don't know the name, but okay, so but the message here is that you have this C star is the closed form solution for this problem. So phi star is the delta hedging, right? You compute the PDE. So this is the Markovian problem. Okay, so okay, so the idea I want to implement a scheme in this problem. And I will compute the optimal control. And my discretization scheme. And then as a byproduct, I will give the C star. Sorry, I will give the result of this infimum. Okay. And when you compare, so this is the numerical result. C star is the theoretical value, and CK star is the value what we get from this numerical scheme. And yes, I think this is a good numerical results. And so some illustration.
Alberto, but you can compare also to the classical Euler scheme to solve this problem, no?
Yes. Yeah, but it's a good question. Yes, but you have problems when you try to solve this. So okay, so there are two things. The first one is obviously you can design a numerical Euler-Mariam scheme in discrete times. Okay, but when you try to use this discretization scheme in the stochastic control, unless you have a Markovian structure, you are not able to do it.
No, okay, I know. Yes.
And so the situation here is so I'm considering not the Euler-Mariam scheme, the scheme that we have constructed.
Yes, your scheme.
Yes. But yes, you're right. In terms of the controlled state, you can design an Euler-Mariam scheme. Yes. Okay. Okay, so in the simplest case, just to finish the talk, in the simplest case of the optimal stopping, so we have Monte Carlo error estimates for the scheme. So far, we were not able to produce to develop a numerical scheme. Monte Carlo, sorry, error estimates for the general stochastic control problem, but for the optimal stopping, yes, we have some answers in this direction. So in the optimal stopping, you know, I mean, the problem is the soup of this expectation here, and the controls, they are just stopping times, right? Okay, you know, I mean, our interpretation is, as usual, consider the filtration generated by the Brownian motion. So F is the Brownian motion filtration. So this capital T here is a set of optimal stopping with respect to the Brownian motion filtration. So this is the Snell envelope. And okay, so the same way that we did in the general stochastic control problem, I can also make in this particular case, discretize everything. The reward function, I discretize in terms of some embedded structure, and the optimal stopping, I consider only optimal stoppings in this, stopping times in this form. Okay. And yes, and then I can repeat everything that I did in the previous slides in this optimal stopping problem. So V, you can determine by standard dynamic programming algorithm in the optimal stopping. So there is a huge literature on this topic, discrete time optimal stopping. And so the error estimates for the Monte Carlo is, so this notation here is going to be very heavy. So I make use of the, people call it learning statistical theory. People call it machine learning, blah, blah, blah. So I'm not really specialist in this topic, but so the way we solve the problem is the Monte Carlo error estimates is making use of the machinery coming from learning statistical theory. So we select a set of space of functions in L2, and so I consider the Monte Carlo samples, and there is an assumption in this stream of literature they call VC dimension, which encodes the complexity of the family of space that I'm going to use in the regression method. Right, and then I will call it VC H. H is the set up of space of function that I choose a priori to work in the regression method. And yeah, so the continuation value in this optimal stop in discrete time one is given by this. So the idea is to make use, for instance, Longstaff-Schwarz algorithm to compute this regression functions. So this is the classical dynamic program principle in optimal stopping. You can write the continuation values, continuation region, and yes. So the Monte Carlo, the theorem 6 is so this is the rate of convergence, which depends on this object here, on this quantity, which depends on the choice that you made when the space, they call it architecture space, and to use in your regression method. So you see, it depends on capital N, encodes the number of the Monte Carlo simulation. K is fixed, and depends on this object here. So then it's not difficult to see that under some regularity condition on the space H, we will get an explicit rate of convergence in capital N. So if we will consider if you assume that the continuation values, discrete time ones, are in the Sobolev space, then and you choose H, the architecture spaces, just a set of bases for your regression method as polynomials with this grow condition, then you get rate of convergence with respect to capital N. And V hat is the Monte Carlo object associated with VK0, which is the optimal payoff associated with the optimal stopping time problem. Okay, so some references. So most of what I explained here is based on this work. It's on revision. It's on archive, and this work is based on this papers. And the optimal stopping case, which is treated in these two papers. So thank you very much. And I think that I should stop here. Thank you.
Thank you, Alberto.
Okay.
we have time for some question or comments. Ernesto did some in the talk, but if other wish to ask. I have a very open question.
Yes, please.
What is the difficulty of change to other process, not related with the fractional Brownian motion?
Yeah, so the fractional Brownian
For example,
motion is
for motional kernels, this type of things.
yes. So the methodology, it's you can work with this methodology in functionals of the Brownian motion. In a particular case, would be the fractional Brownian motion.
Okay.
And the fractional Brownian motion, it's so yes. So there is an explicit dependence with respect to the Brownian motion. And this particular kernel here is not really important.
Okay.
You can work in other types of kernels.
Okay, thank you. Ernesto.
I have another question. In the optimal stopping case, how the dimension of the space plays in your rates? Because you have Monte Carlo.
Yeah.
I mean, it is difficult to solve high-dimensional optimal stopping problems. Very difficult, so to say. Can your method give some answer in this?
Yes. So this is the dimension of the problem.
But because this is the number of steps, A?
Yes. Yes. Because K is fixed.
Yes.
K is fixed. And so you fix K. And so the number of factors, so this is the number of factors here. The steps of the Monte Carlo, it's given by capital N. And so K, it's very large. So it's a high dimensional problem, yes. It's a high dimensional problem, but at least you can treat by today, especially today, by means of the computers, right? But it's very high dimensional problem. Yes, it's very demanding, and since we have this, because I didn't have time to discuss here, but similar to the general stochastic control problem that we have discussed. So we have the rate of convergence on the level of the Brownian motion discretization, and we also have rates when you consider the Monte Carlo discretization.
Mm.
So when you combine these two, then you are able to control the number, the dimension of your Monte Carlo scheme.
Okay.
And it's very high, yes.
And do you have examples in your papers of two-dimensional or three-dimensional optimal stopping problems?
Examples in the sense that I consider this problem here, and I show the rate of convergence in this paper here. I show the rate of convergence not only with respect to the Brownian motion.
Okay.
And here is the Monte Carlo error estimates. And some examples with path-dependent SDEs.
Mm.
Because this regularity condition here, it's not obvious that it's satisfied in concrete examples. In the fractional Brownian motion case, no, we haven't worked in these two papers here.
Okay, thank you. So optimal stopping for fractional Brownian motion, there is no answer yet, so to say.
No, I think that I have the answer. I have one answer, but as we discussed it before,
yes,
the answer it's a numerical.
Okay.
It's a numerical answer, but I don't believe that we agree about this. I think.
Yes. We discussed this. Okay.
It's impossible to get
no closed solution. Yes.
Yeah, closed solutions, and then this solution, it's reasonable to give, no, because since it's I mean, this kind of problem happens also in the Markovian case, so it's very rare to find a closed solution.
Yes. I wanted to know if there are no new results in this direction.
So there is a paper by Frédéric Variance and Jianfeng Zhang. They work in this path-dependent PDEs, but there is no numerical scheme for that. So.
Okay. But they consider optimal stopping for fractional Brownian motion? No. Okay. No. This is okay. Thanks.
There is a paper you told me there's with some mistakes, right? But
yes. But this is very old. Who works on? Okay. No, I simply wanted to know if there are new things in this field because it's an interesting topic. Okay. Thank you for your answer. Thank you very much.
Thank you again for Alberto.
Okay.
Thank you very much. Yes.
I stopped it.